This is really a very, very early concept phase study. So we're looking at something much, much less concrete than what we just saw from SOX and Foremost. And of course, we're super excited about these ongoing projects that will be essentially telling us a lot of the developments that we have going forward with this facility. So just to give a quick shout out to the project office involved, Roland Bacon is the lead coordinator of this project, and Sophia Randish, the deputy. Vincenzo Manieri is currently the project scientist. I do want to stress that this is a very early phase sort of concept study that we're doing. This is not an ESO facility. Just want to be clear about this. We are in consortium and a science group defining this facility at the moment. And we recently put together a big science team, now has 485 members that are contributing to this. The overall spread is in 4 different work packages on the time domain, as led by myself and Cyrielle and Paula, who are here. You can, of course, also talk to the 2 of them for more information. We have a galactic science case, a cosmology, and an extragalactic science case. Right, and here's the shout out to the 2 deputies. So on Tuesday, there was this really awesome talk by this guy called Richard Anderson, and he said, well, spectroscopy will be the key bottleneck in the follow-up of the LSST era. And this is exactly where we're gunning for with WST. Also answering a call from the AstroNet roadmap, where it was stated that we need a dedicated 8 to 10 meter facility that would enable spectroscopic follow-up in the James Webb, Rubin, and Euclid era. So think of WST maybe as a deep, wide, fast facility dedicated to spectroscopic observations in the optical in the era of polychromatic sky video. And just to show you that this is a little bit more concrete than just words, we even have images of our facility. Here on the left, you see the dome structure, and on the right, the telescope. This would be a segmented 12-meter telescope. I have some more top-level requirements for you later, with an IFS coming out of the Nasmyth platform and a fiber positioner and a corrected Cassegrain focus. So basically, we would have these 2 major instruments, a very wide patrol area of 3.1 square degrees. At the moment, we're hoping to get to 4.5 square degrees, if that turns out to be possible, where there would be a MUSE with 20,000 low resolution and 2,000 high resolution fibers patrolling this area. And in the center of this, there would be an integral field spectrograph that would measure 3 by 3 square arc minutes in at any given time. That's 9 times the area of MUSE, and that could do mosaicing of 9 by 9 square arc minutes. And of course, what we're really hoping to do here is to operate these 2 in tandem so that they can really operate simultaneously for maximum flexibility and impact. And the reason why we were interested in combining a MUSE and an IFS is because they're a very complementary type of instruments. And in particular, apologies for the text here. In particular, you can look at this by comparing the candles good south field that was monitored with a MUSE. Here in red is the redshift and magnitude distribution compared to the MUSE Hubble Ultra Deep Field that was targeted with MUSE. You get really complementary information. MUSE is able to go deeper, to go to larger redshifts. And so by combining the area from a MUSE with the depth of the IFS, we think that this will really be a very important addition. Furthermore, an IFS can do a lot of things that regular photometry cannot do, in particular to figure out faint sources where broadband photometry may not be sensitive enough to find emission lines, for example, at very specific wavelengths. And so this would be targeting things like ionized emission in the circumgalactic medium and the intergalactic medium, and of course, lots of serendipitous discoveries. With this kind of facility, we do want to be open to all the possibilities. We don't want to bias us too early. And so we really think that this large of an IFS on a dedicated 10-meter facility would really be a major plus. So here's a quick rundown of the spectral resolution as a function of wavelength that we're envisaging. This would have 2 paths, so you're basically covering the wavelength range of blue MUSE and MUSE at the same time with comparable spectral resolution. This, of course, is a major investment. There's 138 spectrographs requiring 276 CCDs. So this is not a cheap facility, as you may imagine, but something that I think is extremely cool when we're combining the IFS together with the MUSE. We can actually track potentially at different speeds the IFS and the MUSE, and this would enable things like measuring a comet at non-sidereal tracking while observing with the MUSE in another field. So just, we're dreaming, so this would be a wonderful opportunity to combine these types of science cases. Now, I mentioned we would have 2,000 high-resolution fibers. The resolution that we're gunning for here is 40,000. That's double of foremost. And this is really driven by the wish of being able to separate as many lines as possible in order to get full spectroscopic information on a maximum number of sources. And so some of the numbers that we've come up with so far is that we would get full chemical information down to a Gaia G-band magnitude of about 16.5. Certain elemental abundance is about 2 magnitudes fainter. There's more numbers to give if you want, but essentially one point I'd like to stress for time domain related studies is that the RV precision is something we're still thinking about quite a lot because this is of course difficult to do in a facility like this, but it could also really be a game changer if we were able to push this to, well, let's say below the 100 meters per second or so. Then we would have 20,000 low resolution fibers. By the way, the fiber design is not yet decided. There's different options on the table from AIP, from APC, and from UCRI, is it? Sorry. But basically, this would really be the transient machine. I mean, that's also why TIDES is focusing on the low resolution spectra, of course. We would, currently the estimate is that in a 1 hour, we would get a signal to noise of 3 per angstrom at a G magnitude of 23.5. This would really be a pretty good match to LSST. And because we have so many fibers, we actually plan to have a fiber level TOO at every pointing that can very flexibly follow up transient sources, and for the time being, we're considering about 1,000 fibers per pointing that would be able to follow your favorite transient sources. This would also be a real radial velocity machine, in particular for white dwarfs. So this would really be fantastic for these types of science cases. And of course, we also want this to be a TOO facility. So both for telescope level when we're really pointing to a new field for kilonova follow-up, or on a fiber level. So how does this facility compare to other ongoing or planned facilities? We have here on the left the number of fibers. I'll use the, if I can work this out. Here the number of fibers on the MUSE and the low res versus the telescope aperture. The size of the symbols here is showing the étendue, so the product of field of view times the aperture. And of course, we're trying to make this really a transformational facility, so we're dreaming big, and this would put WST really up here in a very interesting parameter space. Of course, MSE is also a very interesting facility that is considered for the north. Both of these kinds of facilities would provide somewhat similar performance here, although the étendue of WST would be larger. And MSE does not currently feature an IFS that would operate at the same time. And this IFS facility, as I said, would really be particularly exciting here. So if we go to the top level requirements, the plan is to reuse ELT type segments. There would be about 78 of those that would make up a 12-meter focal plane. The spectral range that is accessible by this optical setup would go to about 1.6 micron, but for the time being, we're targeting only optical wavelengths out to 970 nanometers, and this is a cost-driven decision, but we are, of course, considering an infrared upgrade in the future because this would be exciting for many science cases. And important to this community, we're really trying to think about the time domain from the start. So we're including telescope level and fiber level targets of opportunity observations in the top level requirements. So where does this project come from? There was a SpecTel study commissioned by Richard Ellis and submitted to the Decadal Survey in 2020 that we're of course heavily informed by. And there was also an ESO community poll in 2020 that Antoine Méran published in the Messenger. And there really is this established need of having such a facility. So in 2021, a consortium of countries shown here got together to apply for EU funding through a Horizon project to try and define this a little bit better. And while we were very well considered, we unfortunately quite didn't make the cut. So we're in the process of reapplying for this funding. So we formed community working groups As I mentioned, we have lots of people now contributing that allow us to, on the one hand, build excitement in the community, really listen to the community and its needs, because this, of course, would be a major facility that would serve a diverse range of needs. And so we're really developing this. The resubmission will be soon for this project. And if we're successful with this, then we could really start the concept study in 2025. And while our goal is to eventually hand this over to ESO, because it's a way too large a program to do for such a small consortium, I do want to stress again, this is not currently an ESO facility. We're at the moment in the process of writing the white paper. And of course, if you still have some things that you would like to add, now is the time to please do it. So with WST, we will provide, or we would provide, really crucial ancillary data for the time domain, even if we're not working in a time domain or a TOO set, right? We'll be targeting lots and lots of galaxy redshifts, about 90 million over 18,000 square degrees from redshifts 2 to 4.5, the 3D density distribution of 6 million galaxies in a narrower ranges, and of course the connections to multi-messenger astronomy there are absolutely fantastic. Then stellar abundances, really down to faint magnitudes, are important for everything from exoplanets to asteroseismology or figuring out chemical evolution of the galaxy and the distance scale and so on. And then, of course, even with the IFS, you would get really interesting snapshots of the galaxies that host important transients, so you could understand the environments. But let's now go to what we're trying to do in terms of the time domain. And of course, we're trying to really make this a significant leap for spectroscopically mapping the variable sky. So we're considering essentially all the scales that we have at our disposal. I already mentioned that we would be targeting comets. We're also thinking of exocomets in this context that would be using the IFS and the MUSE. On Tuesday, I spoke about the huge range of types of stellar variability that one can study, and a lot of this requires spectroscopic information, either for classification or for searching for radial velocity variations, for line shape variations, and so on. Then we would have primarily fiber level TOO for the typical type of transient sources, where we would be informed by the brokers you guys are all creating and your projects, whether it's stellar flares, supernovae, TDEs, GRBs, and so on. And we're also very interested in following up compact objects with radial velocities, in particular to understand the supernova progenitors, for example, but also to detect stellar mass black holes that are not X-ray binaries. And then last but not least, the even more compact objects, gravitational wave events with electromagnetic counterparts. These would really trigger telescope level TOOs, where we would probably focus with the IFS on the most likely region and then try to map out the other galaxies or possible counterparts with the MUSE, because in the other area of LSST, there will be so many candidates in this particular region that having that early spectrum will really be powerful. And in addition, white dwarfs could help to serve as gravitational wave calibration sources, continuous sources for LISA calibration. And last but not least, we would also go, of course, to supermassive black holes by the word I can never pronounce, reverberation mapping. There we go. And of course, quasar variability. So you see, it really covers all the scales. We're looking at a huge range of timescales and science cases. And last but not least, we of course want to be open to all the various beautiful things that will be discovered in the meantime. So we want to be flexible to maintain that serendipity. One way of I realize I'm going way faster than I thought it was going to be. So one way of looking at this is that we can see in this parameter space opened by WST, we can look at different types of variable or transient sources as a function of the spectral resolution that they would need and the function of the cadence. And so this is a little bit what informed our choices here. But of course, this will be a trade-off. I mean, you also have to be realistic. We have 20,000 fibers. That's not the same as, I don't know how many gigapixels LSST has. And the typical exposure is much longer. So the trade-offs are there. What I'm excited about is that there's many different surveys happening at the same time on WST. There's cosmological analyses, extragalactic, galactic, and so on. But there's really this will of working together to make time-resolved measurements possible with this facility. And so, for example, as we're mapping the full southern sky to measure redshifts of galaxies, we would be splitting the exposures in a way that you get time resolution for these measurements. Then, of course, we can target specific smaller areas like the LSST deep drilling fields or Rubin specific, Nancy Grace Roman fields for more detail. For stellar variability, we would probably be targeting the Magellanic Clouds, maybe parts of the bulge. So these types of trade-offs are being considered. So that already brings me to my conclusions. I was much faster than I was planning to be. It gives us more time for questions, I guess. So with WST, we're really going for an unmatched spectroscopic capability in the era of this panchromatic all-sky video and multi-messenger astronomy. The top priorities of all the major planning exercises combine these two things, time domain and multi-messenger astronomy, and it's pretty clear that we need additional spectroscopic capabilities, so that's why we're really excited about this project. We think that this setup that I just presented to you brings multiple multipliers to the table, the simultaneous ability to run an IFS and a MUSE, the multiplexing, of course, the size of the IFS, the étendue of the facility, resolution that, of course, you cannot reinvent afterwards, and also the flexibility we're trying to build in from the start. So this could really be transformational for astrophysics and cosmology and would complement ESO's suite of facilities for the 2030s quite nicely. There was a cool talk the other day about generalists and specialists, and I think this would make ESO go a little bit more on the side of the generalist in a very nice way. So we're trying to build in this time domain mindset, but in a facility like this is no easy task. Of course, we're specifying this in the top level requirements, but in terms of the operations, this will be quite difficult. There was a talk by Matthew Graham that I found extremely inspiring in terms of maybe in the future it's going to be a robot deciding what we do, so maybe operations won't be as difficult. Of course, we will be listening to the brokers as this comes in, and there's so much development. I've just been fascinated by the things I heard yesterday. So much development on this that I think planning right now how to do this is not even feasible. I mean, we're still going to learn so much in the next time. But what we do want to do is to do very rapid data reduction and very fast dissemination of the results in order to really make this fit in nicely to this kind of LSST era. So of course, WST will not only listen to alerts, it would also issue alerts. So things like anomaly detection would be processed on the spectra as they're being collected. So we really will also try to go down this road. And so fingers crossed for the Horizon call. If you're interested in joining the WST science group, this is of course still possible. Here's the website. We want to get the whole community involved in this. We want to get your opinions and to make sure that we're really designing something that will make sense for the, let's say, late 2030s and 2040s. And we're also a really nice group of people that go to nice places. So here's a picture of our busy week in Verena. Thanks very much.
Thanks, Richard. Any question?